Hello. Uh, Hi. So the topic for today is thread attributes in POSIX. In previous video, we studied about basic thread operations that we use in POSIX and how do we use them and what are their objectives. And during that conversation itself, we pondered upon another thing. We came up upon the concept of thread attributes, and I said it's a little advanced and we may be doing it later. So today, here it is, we are doing it today. And so we will study a little bit about what thread attributes are and what are its objectives, and we will be studying how to implement them, how to get the best out of it. So again, we shall be using POSIX library, and let's start with it. So first things first, objective. As I usually say, that in anything we start with the objective. So the objective of having this implementation, this concept of thread attributes is it's an attribute of thread. So if we want our thread to work in a particular fashion, then we are going to use some of the functionality provided by POSIX library, that is called attributes, and by those attributes we will specify how we would like this thread to perform. For example, one of the attributes can be whether uh, you know its state, what kind of state we want for a thread. Do we want to wait until the thread ends, or do we just let it be? And such questions will answer. Another thing could be like, for example, let's say we would like to specify a scheduling policy. Some threads may be more uh, you know should be prioritized more over the other threads. Our implementation maybe, so our solution may be working so that some threads are more important than others and require more CPU cycles to be allocated to them. In that case, we can specify that this thread has more priority, or its scheduling policy would be so and so. Or we can play with the stack size. For example, if we initialize a thread with default attributes like we did last time, then it will have a default stack size, and sometimes it may be overwhelming, because sometimes, okay, of course, your thread may need more than the default stack size, so you would want to increase the stack size. But it could be the other way around also. For example, you have an application that you want to scale to thousands of threads, let's say, and each thread is being allocated with 1 MB, or let's say whatever default size is, that size of stack, and it may overwhelm the system. You may not need those threads to use that much memory every time a thread gets spawned. So you can also decrease the stack size when you want to spawn a thread. So these are the attributes. They give us flexibility to define how the thread, after being created, should perform, in what manner it should perform, what kind of resources, how it should use the resources, etc., etc. You will understand more as we go on. So I hope the objective is clear. Okay, now today we shall discuss how we set the attributes of a thread at the time of its creation. Why specifically creation? Because it's the only time where we can modify the object. Once we create the object, you must remember that in pthread create call, we had something called start routine. So once we are done with that, then the thread starts executing, and once the thread starts executing, you cannot change its attributes. You cannot change its attributes once it has started executing. So attributes can only be specified at the time of their creation. They cannot be altered later on in the program, in the code. Okay, so excuse me. Another thing is that I'm going to give you a general, series of steps now that will always be how you work with attributes. Okay, so in general, what you would do is, the step one would be to create an attr object, attribute object, and call pthread attr init. What this will do, this call will initialize the thread attributes by default values. Okay, it will initialize the attributes with default values. Second step would be to call a series of functions that are provided to us, known as pthread underscore attr underscore asterisk. So asterisk here represents that it could be many types. As I said, we can change scheduling policy, we can change scheduling priority, we can change stack size, we can change the detached or undetached nature of the thread. So for that, there would be multiple functions. One would be pthread attr underscore sched something which is scheduling related, or underscore set detach state. So that would be setting the state of the thread, etc., etc. And the third step would be to do a pthread create, which we had studied in earlier class. So the idea is this only. You initialize the thread with default values, you change the attributes, whichever attributes you want to change, through these types of functions. We will study the exact functions in a while. And then you make a call to pthread create, so that the thread gets created and starts executing from the start routine that we are going to provide. In general, the code would go basically like this. You will create a pthread attr underscore t object, let's say tattr. You will create this object, you will initialize this object, pthread attr init ampersand tattr. Using this function, we covered this in the previous video also. Then you would call pthread attr setting some attributes. You will provide what an object you are going to change, it's the same object, and some attribute value. That is how it will go from here on. Sorry about the interruption. Okay, another thing we need to understand about the attributes is this, that attribute object is always opaque. So what I'm trying to say is, I'm saying attribute object, which I just showed you, it's opaque. What does that mean? What does that mean is that they can be directly modified through assignment, right? If we had to set the scheduling, let's say scheduling method to, let's say, round robin, then we cannot simply say that attr dot policy equals to sched rr. That would be wrong. they are not exposed this way, so we will not be able to do that. What instead we will have to do, we will have to use the attribute setting functions that we have already discussed. Okay, now so the thing is, the attribute object which we just declared like this, if you remember, p attr something something underscore p thread attr underscore, this is very good, p thread attr underscore t attr, which we just declared. This, once the thread is done executing, this object will still keep on taking the memory which was allocated to it. So this object needs to be destroyed once its needs are met. Let's say a thread, parent thread was p thread, uh, parent thread was pair thread, and it spawned something called child thread. So once, and it used tattr for initializing the child thread. So once child thread is done executing, and let's say exits, it's basically destroyed, the tattr is still present and holding the memory, it's holding it. So for that we have a function provided by POSIX that can destroy the attribute objects. The function goes something like this: return type is int, which if returns 0 means success, any other values means error. Pthread attr destroy attr destroy, and it takes attr object, of course, pthread attr t asterisk tattr. So once you are done, you want to destroy the attribute object, to make a call to this function and it will destroy the attribute object. Okay, since okay, moving on, now we will study the attributes in details and the APIs that are provided by POSIX and how to deal with them. First up, quite very important, is detach state. Okay, so detach state can be of two types. Okay, either it could be pthread create joinable, or it could be pthread create detached. Okay, it could be either one of these. This is the default one. If you have created a default object, or if you are passing null through, instead of attribute object, through pthread create, then this will be the detached state of your newly created thread. And otherwise you can specify this pthread create detached state, and in that case the newly created thread will be detached. This one is non-detached. Now the function call that you will use to do these operations is int, of course, is the return type, and it runs 0 in success case, otherwise errors. and the API name is pthread attr underscore set detach state. And it takes two arguments. One is pthread, the attribute which you are changing, and an integer value of, let's say, detached state. So in here you can pass either one of these, pthread create joinable or pthread create detach. Usually it will be an int value, not a reference. Okay, so in that manner you can pass. I believe this is clear to everyone. And it has a cousin also, this function set detached state, wherein you have a get detached state, wherein you can supply the reference to again attrt tattr and a reference to an integer value, an integer variable that will collect one of these two and provide you with the information that this particular attribute has this detached state in it. Okay, now the big question, what do these two mean? We saw that detached state is can be these two offered by POSIX, and this is default, and we saw the APIs that can set this value or that can read what the detached state is. But what they actually do is that in case of pthread create joinable, it is assumed that the calling, so for joinable it is assumed that calling thread will wait for what? Until the thread completes execution. So it is also expected that the calling thread will actually implement a pthread join. If a thread is created with pthread joinable, then that particular thread, when it terminates, its exit status is kind of saved, it's preserved, so that it can be supplied to calling thread when it calls pthread join, let's say, and it is assumed that the calling thread will wait for it. I mean, it's like the calling thread will not go out of its own execution unless it has ensured that the spawned thread has done is done with its execution, in case the detached state is joinable. If the detached state is not joinable, but the other one, what was the other one? Other one was detached. So if it is detached, in that case, in that particular case, the thread terminates and the calling thread will not have to wait for it. Basically, uh, uh, in case we want to spawn a thread and we don't want the main thread to block its execution for it, we are just sure that it's a small task, this newly created thread will perform without any problems, it has no pitfalls or anything like that, so it will perform and it will go out of its termination, and we don't want to wait for it, we can create a pthread create detached. So the resources of a detached thread, if a thread is detached, then whatever resource it has been holding, or the thread id that pthread create return, everything can be reused. All the resources will come back to the main the caller function, and the thread id also again can be reused, and the caller function will not have to wait for it to complete its execution before terminating its own execution. So that was detached state. Another attribute is thread scope. Thread scope. Okay. So thread scope, either a thread can be bound or unbound. Okay. What is bound or unbound? A thread is called a bound thread in case uh, it's a system scoped thread. So the value that we use for it is pthread underscore scope underscore system, or we call it unbound if it is pthread underscore scope underscore process. Okay, so we have two functions for using these. Again, one is int is the return value, and I think by now you understand that 0 is success case, and pthread underscore attr underscore set scope, and again we shall provide an attribute, I believe you know the type by now, and an integer value. Scope is an integer value. One of these two we will provide to set the scope of this particular thread, and again it has cousin that would be get scope. Again we will provide attribute and a reference integer so that it can collect what the scope actually is. And again these two values. Now the big question, what do these two values mean? So in case the thread is, let's say, unbounded, then the scheduler would choose the parent process for scheduling, and once that is done, then the threads will compete within themselves to be scheduled basically. So if the kernel offers, let's say there are three threads, and kernel offers two lightweight processes, LWP1 and LWP2. So these three, if they are all three unbounded within the process, so once the turn of process to be scheduled comes, then these three will have a many to many relationships here, and they will compete for these two lightweight processes for their execution. But if it's a bounded thread, let's say the third one was a bounded thread, then it will be allocated a single LWP. Okay, it will not compete with these two threads. Its competition basically is with the all the threads in the system, right? It's not within these uh, it's not bounded by within this process it is not bounded to compete for the same resources. So basically the thread scoping, bounded or unbounded, defines this behavior, wherein whether the thread the newly created thread will compete with the other threads in its own process, or it will act like as a separate entity in the eyes of the scheduler to be scheduled. So that's how this works. And moving on, I hope this was clear. Moving on, we have a thread scheduling policy. So thread scheduling, this is good. Thread scheduling policy. Okay, so POSIX defines these scheduling policies that we can change through the attribute is scheduling FIFO, or it defines scheduling RR, or it defines scheduling other. Okay, so this is an implementation defined method. This is implementation specific. So what happens is, when we are creating a new thread, we can ask the new thread to have its scheduling policy as first in first out, or round robin, or other. Again, what will be the default policy? Default policy will be the policy that the parent thread has assumed. If the parent thread is using RR, then all the threads spawned by it will have scheduling policy as RR by default. We can of course override that. And first we will see the API, and that is used, and then we shall see, okay, what these mean, what these have to offer, the different policies. So the API is, again, return type is of course int, 0 is success, and pthread attr underscore set sched policy, set sched policy, and it of course takes an attribute and policy, an integer defined by the macros I just wrote a minute ago, sched underscore RR, or sched underscore FIFO, or sched underscore other. Okay, so simple. And it would also have a cousin, in case you are interested, get sched policy, and by now I think you understand how that would go. So now what do these different policies mean? So the sched FIFO would mean, let's say there was a thread, and we, before creating it, we provided it with an attribute of sched FIFO as its scheduling policy. So how it will behave is that this thread, once it has gotten hold of the processor, let's say kernel, then it will run. This thread will run until either it's preempted by a higher priority thread or blocked. Okay, so this is either preempted by higher priority thread, or it is blocked. What does blocked mean? So basically there could be multiple meanings of blocked. Either it's waiting for a resource, or the process itself has been taken out of scheduling, and some other process has got the processing slice, let's say. So In these two cases, the thread would, you know, be preempted. It will other than these two conditions, it will keep executing. Now the scheduling RR, what does that mean is, what does that mean is that it can be, so higher priority thread starts running when the process gets uh, when the scheduler, the system scheduler, chooses the process to be executed, then inside that process the thread with highest priority starts executing. Okay, and it keeps on running until it's preempted by a higher priority thread, so these conditions stays the same, or it is blocked, so this condition also stays same. An additional condition is that its time quantum that has been specified has been has elapsed basically. So the time slice, as we all know, okay, round robin means that the process will keep on sharing the, you know, CPU based on time slices. So once the time slice is expired, another thread will get to execute. So only that changes in RR compared to FIFO. Okay, and the third one is, so basically new concept was time slice, and basically the last one was sched other, and that means that process is saying I don't want FIFO, I don't want RR, I want some other type of scheduling between the threads that I am going to implement myself. Okay, for example, some application may want the threads to work on demand. Okay, it doesn't want the thread to, you know, keep taking the time slice of the time quantum or anything. It doesn't want to do that. It wants them to execute or perform on an on-demand basis. So in that particular case, it may specify a scheduling other and do its own implementation, how the threads that it has spawned may be executing, in what manner they would be executing. I hope that is clear. If not, just let me know. And another one is scheduling priority. Okay, now we have spoken that, okay, the, let's say in case of RR, we start with the highest priority. Okay, and in case of FIFO also we've spoken that one thread can be preempted by the thread of higher priority, the other thread of higher priority. So how do we set the priority? Okay, so now the question comes, setting thread priority. Okay, so to set the thread priority, I'll give you a 3-line code, and I believe you're smart enough to figure it out how it's working. Okay, so there is a structure called sched param that is provided by POSIX. Sched param. So what we shall do first is we shall define an object of type sched param. Okay, then we will say that param dot sched priority and we will provide an integer value. Higher the value means higher the priority. Let's say we provided a priority of 30. Okay, and then we will make a call pthread attr sched param Okay, please check it again. It could be set sched param also. Okay, please check it. Okay, it could be sched param or set sched. Again, we shall provide attribute and a param value. Param value here is not going to be an integer, it's going to be a value of sched param type, which we have assured here. And that is how we shall set the scheduling priority in param, in attributes, thread attributes. And once we create a thread using pthread create, using that attribute, then it will have a scheduling priority of 30. So this was about the attributes. There is one more actually, and it's about stack. So it's stack address or stack size. We actually did discuss about stack size a little bit earlier, wherein I gave an example where the default size of stack may be too large, and if we are spawning thousands of threads, we don't want to overwhelm the system memory, so we want to keep it small. That is one use case. There can be multiple use cases, but the thing is, I am not going to cover that stack size attribute today. I have not seen it being used all that much, and it's a little advanced. All this is a little advanced, material than generally I have seen being used. But stack size is something that I have not seen being used much. Also, granted that many of you will find motivation to go through stack size by yourselves in case you are curious to know, or it comes your way, then you can, you all are really smart enough to go through the stuff and figure it out for yourself. So stack size I am leaving for yourselves. Those who want to understand it, they can find a way. Other than that, I'll be finishing it today, this class here. Um, so to recap, we did discuss about the thread attributes of threads provided by POSIX. So what is the objective? First of all, we studied that why do we need attributes at all, and we understood that it is to ensure the behavior of thread as we would like. And then we went through multiple attributes, and for each attribute we went through the APIs that are used. We went through the flow in which we should be using those APIs, and we understood the meaning of each attribute, what it does and what values it offer, and what each of the option that it offers, how it impacts the thread behavior. So from me, this is it for this particular class. Let's hope we shall meet